Okay, so today we're going really small, like subatomic small. We're talking about electrons. You know those tiny things that make our electronics work? Well, imagine them just frozen in place, but still somehow letting electricity flow. Sounds kind of crazy, right?
Yeah.
But it's actually happening. It's cutting-edge science, and it's straight from the pages of Nature magazine. So we're going to deep dive into some graphene research today. But there's a twist, and I mean that literally.
Intriguing.
So first things first, what exactly is graphene?
Well, graphene is already a pretty amazing material. It's basically a single layer of carbon atoms arranged in this like honeycomb pattern. It's incredibly strong, conducts electricity really, really well. And scientists are already looking into how to use it for all sorts of things, from flexible electronics to better batteries.
You know, I've heard about graphene. It's like that wonder material everyone's been talking about.
Yeah, exactly. It's got a ton of potential. Yeah.
But what really got me excited was this new research where scientists took two layers of graphene and they stacked them together. But here's the thing. They rotated one of the layers just slightly. And that created this really cool pattern called a moiré pattern.
Yeah, moiré patterns are fascinating. They pop up everywhere in nature and science.
It's kind of like when you throw two pebbles into a pond and the ripples from each pebble, they intersect and they create this new, more complex pattern. It's like that.
Exactly. You got it. That's a great analogy.
And this twist in the graphene layers, as simple as it sounds, it totally changes how the electrons behave inside the material. They've actually observed a whole new quantum state, which they're calling a topological electronic crystal.
It's a mouthful, I know.
Topological electronic crystal. It sounds like something straight out of Star Trek. So what's really going on at the atomic level here? How can electrons be frozen but still conduct electricity?
It is a bit of a paradox, I'll admit.
Yeah.
Basically, the electrons in this twisted graphene, they get locked into position. They form this crystal-like structure.
Okay, so no more movement, right? So how's the electricity flowing?
Well, here's where it gets really interesting. Each electron is also spinning. And they're all like spinning together in perfect unison. This creates a current that flows along the edges of the material without any resistance at all.
Hold on. They're frozen in place. But UT also spinning in sync at the same time. It's like if everyone at a football stadium was doing the wave, but they're all glued to their seats. How does that work?
It does seem counterintuitive, I know. But the experiments show this behavior very clearly. And what makes it even more mind-blowing is that the amount of current flowing along the edges is directly related to some of the most fundamental constants in physics, like Planck's constant and the electron's charge.
Right. Okay, so you're going to have to explain that one to me. Why is that a big deal? What's so special about these fundamental constants?
Well, think of it this way. Fundamental constants are like the unchanging rules of the universe. They're the same everywhere. So the fact that the current in the system is so precisely determined by those constants means that it's inherently reliable and predictable. And that's a huge GE deal for something as delicate and as prone to errors as quantum computing.
Okay, I'm starting to see where you're going with this. So this discovery could be really important for building quantum computers that are actually stable and reliable. I always thought quantum computing was way off in the future, like something we wouldn't see for decades. Is this discovery pushing that timeline up?
It's definitely a big step in the right direction. But before we get too ahead of ourselves, let's take a closer look at what a topological electronic crystal actually is and how it connects to this whole mind-bending concept of topology.
All right, let's do it. All right, all ears.
All right, so let's start with this word topology, okay? Imagine you have a donut and a coffee mug. They seem totally different, right?
Yeah, I mean, one's for dunking and the other's for drinking.
Exactly.
Yeah.
But in topology, we look past those obvious differences and we focus on their fundamental shapes. The holes, a donut and a coffee mug, they both have one hole.
Okay, I'm seeing where you're going with this. So topologically speaking, they're the same.
Exactly. They're equivalent. It's all about those properties that stay the same even if you stretch or twist or deform the object.
Okay, so back to our electron crystal. How does a donut and a coffee mug relate to that?
Well, a topological electronic crystal. It's special because its key properties are determined by its topology. In this case, it's the way those electrons are arranged. And that synchronized spinning, they create this unique shape where the edges behave very differently from the inside.
So even if you messed with the crystal a bit, those edge properties, that unimpeded flow of electrons, that would stay the same.
Exactly. It's incredibly robust. That's one of the reasons why this discovery is so exciting for quantum computing. You see, quantum computers, they rely on these really delicate things called qubits, which are super prone to errors.
Yeah, I've heard about those qubits. They're like the divas of the quantum world. Super sensitive.
That's one way to put it. But if we can create qubits based on these topological electron crystals, They might be much less sensitive to noise and errors, so we could have more stable and reliable quantum computers.
So how do we go from seeing this in a lab to actually using it to build a quantum computer? That seems like a huge GE jump.
It is a huge jump, but we have to remember that even the biggest technological revolutions, they start with small steps. And in this case, it all started with an undergraduate student named Ruheng Su. He was working in Professor Joshua Folk's lab at the University of British Columbia.
Yeah, it wasn't some big shot scientist. It was a student, someone who was just starting out in quantum research.
Exactly. It just goes to show the power of curiosity and having a fresh perspective. So Sue was studying this twisted graphene sample that had been prepared by Dr. Dason Waters, a postdoc researcher, and he noticed something unusual in the data. But instead of just ignoring it, he decided to dig deeper. He collaborated with his mentors, and boom, a brand new quantum state was discovered.
I bet there was a lot of celebrating in the lab that day. What I find really cool is that this discovery, it's not just about quantum computing. It could change how we understand basic physics, too.
Absolutely. We're talking about a totally new state of matter here. It challenges everything we thought we knew about how electrons behave. And it opens up all these new paths for research. Imagine what we could do if we combine these topological electron crystals with superconductors. You know, those materials that conduct electricity with zero resistance.
Zero resistance. Wait, that's not just a science fiction concept.
It's real, although the technology is still pretty new. But think about it. Merging those properties of topological electron crystals with the perfect conductivity of superconductors, we could create all sorts of new quantum devices. Devices with capabilities we can't even imagine right now.
Okay, now you're getting me really excited, but let's not get too carried away. Before we start building quantum spaceships, let's talk a little bit more about quantum computing itself. Okay, so for those of us who don't have a PhD in physics, what exactly is quantum computing? What makes it so different from the computers we use every day?
It all comes down to quantum mechanics. Quantum computers, they use the strangeness of the quantum world to do calculations in ways that our regular computers just can't.
Okay, I'm already a little lost. Can you give me an example?
Sure. Imagine a coin that can be both heads and tails at the same time. It's kind of like superposition in quantum mechanics.
Whoa, so instead of just ones and zeros, you have these qubits that can be both at the same time.
Exactly. And that's not even the weirdest part. There's also entanglement, where two qubits become linked no matter how far apart they are. So if you measure one, it instantly affects the other one. It's like they have this invisible connection.
That's wild. Okay, so how do these quantum quarks translate into actual computing power?
It's all about exploring possibilities. A regular computer uses bits, which can be either 0 or 1. But a qubit, in superposition, it can be 0 and 1 at the same time. So a quantum computer can explore tons of possibilities all at once. It's like a massive speed boost for certain types of problems.
So we're talking about solving problems that would take our computers millions of years, maybe even longer, and a quantum computer can do it in like a few minutes.
Yeah, something like that. We're talking about simulating complex molecules for drug discovery, optimizing financial algorithms, cracking encryption codes that protect our data. These are all problems that quantum computers could potentially solve incredibly fast.
That's amazing. It sounds like quantum computing could totally change the world as we know it.
It definitely has that potential.
But let's not forget what started this whole conversation, that incredible discovery of a topological electronic crystal in twisted graphene.
It just goes to show you, exploring the fundamental mysteries of the universe can lead to some pretty amazing technological breakthroughs.
It makes you wonder what other strange and wonderful quantum states are out there just waiting to be discovered.
Exactly. It's like we found a new element on the periodic table. But instead of an atom, it's this whole new way for electrons to behave.
It really is mind-blowing. So for our listeners out there who want to learn more, what's one question they should think about?
Well, if we can create these incredibly complex and stable quantum states in materials like graphene, what other secrets are hidden in the quantum world? What could those discoveries unlock for the future?
It's an exciting thought that maybe one of our listeners will be the one to make the next big breakthrough. So to everyone listening out there, keep those minds curious. The quantum world is full of surprises. Well, that's it for our deep dive into the world of frozen yet free electrons and the future of quantum computing. We'll be back soon with another fascinating exploration. But until then, keep exploring, keep questioning, and keep diving deep.